The next section is about the probabilistic LSA. So the probabilistic LSA means we want to use the probability. Okay. So what is the LSA and MF? They are non-probabilistic. What does it mean by non-probabilistic? We are not using any probability, but we are using the matrix factorization, matrix decomposition to find the topic importance or to find the topic model. The second part, which is about the probabilistic, we try to figure out the probability of the words in our data. So that's why they call it probabilistic LSA. So PLSA or probabilistic LSA, it is a probabilistic model that explains the creation of the documents. It is based on the categorical distributions. Now let's see. When we have the probability, we are using the distribution model. The distribution means how many or how frequent some topics on the document and how frequent some topics on the particular words. So the document topic distribution means documents have its word distribution over the topic. So one document have its word distribution. So for example, the basketball, we have one. And the document one, we have, for example, games. Okay, we have one. So we call this kind of frequency is the distribution. And we want to know the document topic distribution. So we want to check whether a document, what is its word distribution over the topics. And the topic word distribution is the word distribution over all the words. So if we have basketball, so we want to check the basketball over all the words that exist in the document 1, document 2, document 3, and then document 5. So we have D, it refers to the document, and we have Z, refers to the topic, and we have W, refers to the word. In this probability LSA, or sometimes they call it probabilistic LSA, it utilized the EM algorithm, expectation and maximization. So expectation, it means we are trying to get the probability. And maximization means we want to maximize the probability and we want to make the parameter estimation. So E step, okay, E is from the expectation. It means we want to find the posterior probability on the latent variables. The latent variable means something hidden, something that we do not know. So the latent variables, we can say it is the topic. That's why we can determine, for example, K equals to 2. Then it means I want to find two topics or I want to find two concepts. So that's why we call it latent or hidden. And we have the M step. It is to find the parameter. What is the best value when we want to complete this calculation? So we use this kind of probability. Maybe the equation seems too complicated, but the simple one is I want to know the Z. Okay, so what is Z? Z is the topic. Okay. So I want to know the probability of this topic, given that it means I know the probability of that particular document and the probability of the particular words. So this is top and this is word or term. So we can get this formula for this result. It is based on the probability of Z, so the probability of the topic, multiplied by the probability of the document belong to a topic and the probability of the word given a topic. So after we know this probability, we can divide with the total. Okay. So that's why this is the probability. So in short, okay, we can replace with this one. Okay, if you try to do like the derivation, okay, we can do some derivation for this simple probability. So it means we want to check the probability of Z given the particular document multiplied by the probability of the word given a particular topic. Okay. So this is the probability of Z given D is the document topic distribution. It is the probability of topic Z in the document D, and the probability W given Z, it is the topic word distribution. The probability of the word W in the topic Z. Okay, so this one is this thing, and this one is this one. So we can directly derive into this probability. The E step or the expectation step, I will just give you very basic one. We just make the initial value or the initial probabilities. The initial probabilities usually, okay, we set random. So random values like what you saw on the Python file, yeah, we can set the init. So the init, if it is random, then yeah, any value can be set into this number, to this probability and this probability. So for simplicity, let's assume that all the probabilities Z given D are equals for the two topics. So for the topic 1, given the particular document, it is 0.5, and the probability of topic 2, given a particular document, it is 0.5. So similar for the probability of word given a topic. So we assume all words are equal for each topic initially. For example, the basketball given the topic 1, and 0.5. Basketball given topic 2, 0.5. The probability of election given topic 1, 0.5. Probability of election given topic 2, 0.5. So all of them are equal, 0.5 at the first stage. And then we will do the maximization. We have the maximization step. Once we have the posterior probability, the posterior probability means the probability of Z given the document and the word. So we update the topic distribution. So first we update the W given Z. Okay, so the W given Z, it was from the previous, this one. It was from this one. Okay. So we want to check what is the probability of W given a particular topic. Then we can calculate. So we want to maximize the posterior probability. So this probability of work given a particular topic, we can get using this formula. It is the sigma of n. N means the number of that word, the number of the word in the particular document, multiplied by the probability of the particular topic given that the document and then the word. So n d comma w is the number of word in the document, and then we will multiply with what we already did on the previous step. After normalization, well, we repeat the similar calculation for other words and topics. So we will do this one for every word. So when word equals to basketball, okay, we do the calculation. When the word equals to games, so we do the calculation. When the word equals to voted, so we do the calculation, and so on. After all the things completed, then we will check the result. So it is like repetition, expectation, and then maximization, expectation, maximization, until we get the maximum of the completed statistics. That's why they call it the EM algorithm. So let's see with this example. Okay, maybe the process is too complex. I try to simplify it into this example. Let's suppose we have 5 documents. Okay, document 1, document 2, document 3, document 4, document 5. So I have the I love basketball. Let's remove I. Okay. So when you do the exam, I will give you like this text. So I have 5 documents. Document 1, document 2, document 3, document 4, document 5, like this, and then do the pre-processing. Okay. So you can do your pre-processing. For example, you want to remove I for simplicity. That's fine. Okay. Or maybe some of you, Professor, I want to include I because it might be helpful later. Yeah, that's also okay. So that's why later on, your result and your friend's result might be different because your pre-process might be different. Okay. Maybe some of you think that, Professor, I do not want to include is. I do not want to include be. I don't want to include will because it is stop words. Yeah, that's also reasonable. But maybe some of you, Professor, I want to include all of them. So I want to get more representative results. That's also possible. Okay. So make sure when you do the exam, you give a good reason. Okay. Mention a good reason. So this is important when you pre-process the data. Now, let's suppose I just have this pre-process. Love basketball, and then basketball is great. So I remove is, election and help. So I remove the, I remove will, I remove be. Basketball, elected player. So I remove new, I remove was, I remove MVP. Okay. And then many, remove in, remove the, also remove. So the remaining is only people voted election. Okay. Using this one, we can generate the document term matrix. So in the document term matrix, we can see this one, and then it's more complicated. So let's assume we want to get 2 topics. Okay. So the topics means Z1 and Z2. So we can start with random initialization. We randomly initialize the probability for the two topics afterwards. So you will set up these random numbers. So for simplicity, we assume each document is equal to the associated topics. So for this one, yeah, let's assume that all of them are 0.5. The topic 1 given document 1, 0.5. Topic 1 given document 2, 0.5. Topic 1 given document 3, 0.5, and so on. And the same as well like this one. The probability of topic 2 given document 1, 0.5. Probability of topic 2 given document 2, 0.5. So this is initial value. Ini. And for this, yeah, it is totally random. So we can get this table. We can get this table. After we have those table, we can compute the posterior probability. So this is the expectation step. The posterior probability is the probability of Z given that D, W. So the probability of a topic given a document and a word using the current estimates, probability of word given a topic, and the probability of the topic given a document. So for every document word pair, we can calculate this one using the Bayesian rule. What is the Bayesian rule? Okay, so we can use this Bayesian rule. The probability of W given the particular topic and the probability of the topic given a document. And then we can divide with the overall probability. So let's just see one example. Okay, let's see how we can get the basketball. So I want to get the word basketball in document 1 for the topic 1. And this one is for the basketball in the document 1 for topic 2. Okay. And we can just put all the probability. So the probability of this one, we can get using this probability of the basketball given that it is on the topic 1. The probability of basketball given that it is in the topic 1. Multiply by the probability of the topic 1 given that it is in the document 1. So the probability of the topic 1 given that it is in the document 1. So we will do the multiplication 0.4 multiplied by 0.5 divided by the summation. Okay, what is the summation? This is the overall probability from the topic 1 and the topic 2. Okay. So we have, if the basketball in the topic 1 multiplied by the probability of the topic 1 given that the document is 0.4 multiplied by 0.5 plus by the basketball belong to topic 2, basketball belong to topic 2 multiplied by the probability of the topic 2 given that the document 1, topic 2 given that the document 1. So it is 0.3 multiplied with 0.5. So we can get this value 0.57. Now we will do the second. What about if this document 1 and the word basketball belong to topic 2? So the word basketball in the topic 2, 0.3 multiplied by the probability of document 1 belong to topic 2, which is 0.5, and we divide with the overall probability. So the overall probability is the same. It means we want to know if this probability and this probability, which one's higher. So using this formula, the probability that the document 1 with the word basketball to be in the topic 1 is higher than the topic 2. Then we have this value 0.57, 0.43. This is from the initial states. So we can do all the document word pairs. So it means document 1 and basketball, document 1 and love, document 1 and grade, document 1 and election, document 1 and health, and so on, until we have a new probability. So this is the expectation step. After we do this one, we want to check the maximization step. The maximization step, once we have the posterior probabilities, so once we have this probability Z given the document and word, we update the topic distribution. So the topic distribution means what is the probability of the particular word given a topic. So the probability of particular word given a topic, we can use this formula. Okay. So the number of words in the particular document multiplied by the probability of topic given that a document and word. What is it? So let's see. The word basketball. Okay, so let's just use the word basketball. Okay. The word basketball in the document 1, we have 1. So the n of document 1 and the word basketball is 1. Multiplied by the probability of the Z or the topic 1, given that the document 1 and the word 1, which is basketball. So we multiply with 0.57. So we can do this one for all. We have the word basketball in document 1. We have the word basketball in document 2. We have the word basketball in document 4. So I think if we have all the posterior probability 0.57, 0.57, 0.57. So let's say that this is 0.7, 0.57, 0.57, because this is the summation of all documents. Then we get the probability, the sigma is 1.71. Then the probability of the word basketball in the topic 1, it is the 1.71 divided by the total counts for Z1. So this is the total count for Z1. So you can calculate later by yourself. This is 4.41. Maybe I have this one in the next slide. So this is the total count for Z1. It means this is the total count for the topic 1. Okay. For the topic 1. For all the documents and for all the respective words. So we do the similar calculation for all document word pairs. Note that the total count for a Z1 is obtained for the expected value for each word in the document. So the probability of the basketball in Z1, we got 0.387. Yeah, you can have this maximization. Okay, so I give you the example how we can get the 4.41. Okay. So previously, this is 4.41. This is the overall or the total count for Z1. How can we get this one? So this is the frequency. Okay. The document one, we have the word love one time. The document one, we have the word basketball one time, and so on. So let's focus on the basketball. Okay, let's focus on the basketball because we do not have the other calculation. Let's just assume. Okay, let's assume that the word love we have 0.6. The word grade finally, after the calculation we have 0.4. The word election after the calculation we have 0.3 and 0.35, and so on. Okay. So what is the expected count? Okay. So the expected count, so we have the 1.71. This is only the expected count for the basketball divided by the expected count for all the words that we have. Okay, for all the words that we have. So all the words that we have is this one. We have one time in the document one multiply by the probability 0.6. So we have 0.6. And then in the word basketball, we have three. 1, 2, 3. And each of them is 0.57, 0.57, 0.57. Then we have 1 multiply 0.57, 1 multiply 0.57, 1 multiply 0.57. So we have 3. The word grade, we have the probability 0.4. And we have one time and multiply by 0.4. The word election, we have 1 and 1. And the probability is 0.3 and 0.35. So 1 multiply 0.3, 1 multiply 0.35. And then this one we have 1, the probability is 0.4. So we got this one. You multiply this one and this one and this one. So the total is 4.41. So this is the expected count for all the words. So we want to know what is the value after we know the probability for the basketball in the topic one compared to the overall or the expected count for all words in the topic one. So this is a repetition. So we repeatedly refines the probability of W given topic and the probability of the topic given a document by alternating between the E step and M step until convergence. So what does it mean by convergence? So the convergence means the algorithm stop making significant changes to the model parameters. So if the probability is changing very small, then we can stop. Or we can change in the likelihood. So this one is the word topic distribution and the topic document distribution. It is stabilized. So for example, in the step one, in the iteration one, we got 0.25. In the next step, we got 0.251. And then in the next step, we have 0.2505, this one. So it means it is already convergence and we stop. So the change in log likelihood, it means the likelihood of the observed data between document and words given the current model parameters should stop increasing or change very little between iteration. Okay. So if it is always the same value 0.25, 0.25, 0.25, then yeah, we can stop this one or change very little like this one. And the change in model parameters, it means the value of the probability is stable or stop fluctuating significantly after its iteration. Yeah, later on, yeah, its iteration updates the topic word and the document topic distribution based on the soft assignment from the previous iteration. So what is the meaning? Soft assignment means each word in the document to a topic is not a binary decision. It is not 0, 1, but it is a kind of probability. So a word may not definitely belong to a single topic. So it means it is not hard assignment. It is not 0, 1. But a word partially belongs to multiple topics with varying degree of likelihood. So we call this is soft assignment. That's why if we have two topics, topic 1, topic 2, if we have this is 0.7 and this is 0.3, then yeah, the probability shows that it is more likely in the topic 1 compared to topic 2. And because it is probability, then the overall value is 1. So for example, the word like basketball in the document, it might be associated with, yeah, at least if we have the topic 1, given that the document 1 and basketball is 0.57. And the probability of on the topic 2, given that the document 1 and basketball is 0.42. So it means that the basketball is 57% likely to belong to topic 1 and 43% likely to belong to topic 2. Okay. So this is like the conclusion. Oh, I need to do this percent. Okay. This is 57%. So this is the result of this 0.57. Okay, due to the time, maybe I will not discuss in detail, but let me just give you the concept about the LDA. So this LDA, actually, it is another kind of probabilistic model. Okay. And it assumes that both words and topics in corpus are generated by a probabilistic process. So if we have this document, okay, so a word is in a document likely to belong to the same topic as other words of that document. So if this word in the document 1 belongs to the topic 1 and this word belongs to topic 1, so most likely that this word belongs to topic 1. If this word belongs to topic 2 and this word belongs to topic 2, this word most likely belong to topic 2. So it is a kind of sequential process. So what if a document contains a mixture of topics? So for example, yeah, if we have the model. So one document contains, two documents contain the same word. So how to distinguish whether it is in the topic 1 or it is in the topic 2? Or maybe this is more in the topic 2. Okay. So we need to have some preference. Okay. So we can use this LDA to find these preferences. Okay, I will skip this one. Let's just, if you have interest, you can look at this PowerPoint. Let's look at the code. Okay, so I give all the details how to calculate this one. Let's just do the Google Colab. Oh, I think I already opened. Okay. So this is Google Colab for the PLSA and LDA. So we have the NNF, it is from the previous one, and LDA, it is the latent Dirichlet allocation. And we have the count factorizer to calculate the frequency. So we have the documents. So let's make it like simple, this one. And then again, you know, the pre-process, we want to calculate how frequent is one word in the particular document. And then we can do the matrix generation. So we call the document term matrix. For the probability latent thematic analysis, I got this code from one person. So let me just make it like this code without the library. Okay. So this is the simplified version. This is what I already explained to you, how we can randomly initialize the probability at the first stage. And then we do the E step, and then we do the M step. And this one will be the iteration. So it will be a loop until there is no big difference between the probabilities. So at the end, we will get the probability of ZT and the probability of WZ. So this is the algorithm of the VLSA. Okay, you can take a look on this. This one is the same with what I explained before. It is the E step, and this is the max step. So we can get the result, the document to topics and topic to terms. For the LDA, we can just use the LDA algorithm. And in this case, we are making the k equals to 2. So we have this document to matrix and topics to terms. Then we have the result. And let's see. Yeah, this is the document term matrix. You know, the frequency of document 0 with basketball, there is 1. Document 1 with basketball, there is 1, and so on. So this is the result of the PLSA. I think you know how to read this one. The topic 1, yeah, the probability is this value. And for the topic 2, the probability is this value. So because this is higher, then there is a high probability that this document belongs to topic 1. So the topics to term is also the same. You can see that the basketball is highly on the topic 1 compared to the topic 2, and so on. For the LDA, yeah, you can also see the same. They have the value to indicate how big is the certainty of a document belong to a topic. So this value means that the document 1 more on the topic 1 than topic 2, and so on. Okay. And this is the topics 2 term. So the topic 1 and the basketball. So the value is high, then it means the basketball is more likely in the topic 1. If we look at the distribution, Okay, so we can see the distribution of the PLSA and the LDA, okay, like this format. So, yep, we already learned about the topic model, application, and some of the algorithm. Yeah, we learned about the LSA and NMF and PLSA. So I cannot explain the LGA. It is only from the Python. So let's, yeah, if you want to know more about the LGA, you can refer to my PowerPoint. Okay. So this is the end. And